Hello, we are Yıldız Rover team from Yıldız Technical University in Istanbul. We are an interdisciplinary robotics team consisting of members from different engineering, basic science and social science departments. We are proud to introduce to you our team and third generation rover, Gökmen.
Our team consists of 7 sub-teams supervised by the team leader, the technical team leader and the business team leader. These 7 sub-teams are mechanics, electronics, software, science, organization, social media and design, and content writing. The team is primarily composed of experienced members who have previously worked on diverse engineering, space and robotics projects.
Our team has been participating in URC, ERC, ARC and Technofest since 2022. Last year we achieved 22nd place at URC, 2nd place at Autonomous Driving and Control Award at ARC. With the experience gained from previous challenges, we are now ready to compete in ERC 2024 challenge area.
The rover chassis consists of T-slot aluminum profiles, providing lightness, durability and easy modification. The vehicle is about 1100 in length and 1500 in height and 900 mm in width. The rover's weight is 36 kg and along with the mission-specific record installed systems, the weight increases up to 58 kg. Positioned at the rear, the differential bar in the rocket suspension system is made of aluminum profiles to guarantee high bending strength and rover stability. This design choice contributes to a more balanced ride with reduced force exposure. The rover exhibits the capability to climb up to 45 degrees slope with airless CPU tires and brushed DC motors generating 20 Nm torque. The drive system enables the vehicle to skid, steer, turn with minimum vibration and traverse high conditions safely and smoothly.
6 degrees of freedom robotic arm that utilizes a combination of brushed, brushless and servo motors is composed of aluminum profiles, carbon fiber tubes and PLA materials to reduce the rover's overall weight. The robotic arm, measuring 1200 mm in size and 9.5 kg in weight, has the capability to reach 1000 mm to either side, carrying loads up to 5 kg. A cycloid drive made of aluminum providing the main power reduction. A differential bevel gear which ensures both the turning and the upward and downward rotation of the 4th and 5th axis, manufactured from cast polyamide. And finally, a belt pulley mechanism made of TPU.
2 different gripper systems were designed for different purposes and can be easily switched between tasks due to their easy-to-assemble feature. Both gripper systems are connected to the robotic arm with a bevel gear and can provide full rotation. Firstly, an adaptive gripper with flexible TPU fingers is used to ensuring both parallel and rounded grip, along with wide grasping ability. The fingertips are sufficiently hardened with PLA to prevent slipping that may occur due to the slippery nature of TPU. Thanks to the interchangeable fingers, scoop-shaped fingers are used to collect samples during science mission. The second gripper mechanism is specially designed for various tasks to carry objects up to 250 mm wide by moving parallel fingers. By dint of this parallel gripper, bolts can be built during construction tasks.
We choose 6 serial 13 parallel Li-ion battery pack to safely provide sufficient current and voltage to all electronic equipment in rover's electronics box. For safety, we used battery management system, which protects the battery from undesirable conditions.
We designed custom-made PCBs, such as power distribution, motor driver, robotic arm, switching, and encoder, with STM32 series microcontrollers on them. Power distribution board has features such as reverse polarity, an INA current sensor, and fuses at the power outputs. These designs provide overall reliability, better control, and durability to the rover. Considering emergency scenarios, an easily accessible emergency stop button has been placed on the rover, which can unconditionally shut it down.
CAN bus and UART protocols were chosen for wired communication in the rover. A 2.4 GHz omnidirectional antenna was used for long-distance communication between the rover and the base station, and a 5.8 GHz omnidirectional antenna was used for massive data transfer.
We improve our previous work based on deep reinforced learning-based autonomy with 3-dimensional analysis support, so we can easily travel in rigid and sloped conditions. We simulate and train using ROS and Unity under terrain suitable for the competition. Thus, it can work quickly and instantaneously from point to point in all conditions.
In order to increase the recognition performance of markers, a model that generates fake datasets with markers visible at long distances and a control algorithm that will check that these data are detected with the same accuracy for certain periods of time have been studied. When the Aruko tag is recognized, the other state flag required for autonomy is triggered and the approach algorithm runs. A multi-threading supported Qt-based mission planner has been designed in which the outputs of mobility sensor data, location information produced through GNSS or location algorithms, and autonomous driving are visualized and positioned on the OpenRL supported map. This interface can secure itself by introducing compression algorithms to tolerate communication drops and possible network congestion.
Rover's localization system consists of our algorithm based on RNN architecture, which we call Modular Deep Sensor Fusion. This can produce position accuracy even when GNSS is eliminated, using data from depth perception, IMU, and wheel encoders, whichever data is still coming from. When GNSS is used but there is a success rate problem, it can improve its accuracy. The training data set required for the RNN architecture was created with data obtained both by determining ground truth on the vehicle in real life and by producing noisy sensor data in the Unity simulation environment.
The ARM software stack combines the edge transformations and inverse kinematics calculations analytically and numerically. Also, it tested and verified in the Unity physics environment with the PID algorithm on the Arduinos by communication with ROS, or image processing algorithms adding support for semi-autonomy.
We used a custom-built quadcopter drone to enhance exploration operations for science missions. Its primary purpose is to capture images of inaccessible terrain, which will be vital in the development of scientific hypotheses. For safety, it has an automatic return home function.
The science team has been working on the geological and mineralogical formations of the selected area. Wells Marinaries region is studied as in tectonic features possessed by ice, alluvial fans, and crater formations. In order to examine the area thoroughly and determine the most suitable landing site, we used JMORS and observed the rock and mineral types in the area. The science mechanism is equipped with analysis devices and is capable of exploring the area by conducting experimental analysis on several rock types, examining the fossil traces and possible habitable signs. A near-infrared reflectance spectroscopy is specifically selected to conduct measurements in higher nanometer ranges, using image processing that transforms the spectra into wavelength.
To determine the conditions of an unknown environment, we use our gas sensors to detect crucial atmospheric gases such as carbon dioxide, hydrogen, oxygen, and nitrogen, shedding light on our studies. We use a drill mechanism to accomplish the deep sampling requirements and reach a depth of 30 centimeters in the soil. As for the collection of surface, the soil is collected by the gripper using caching mechanisms, scoop-shaped fingers, then poured in the container.
The conditions of the soil are determined by our soil sensors, encompassing the most fundamental nutrition such as NPK, as well as pH levels, humidity, temperature, and methane gas emissions. Additionally, a digital microscope is employed to examine the sedimentary characteristics of the rocks. Our rover is capable of constructing a wall following the requirements by using materials provided at maximum height.